Okay, so I asked you guys to think about a few things. Um, so we can talk about some of those. Do you guys have any questions outside of those that I should address before? Anything like from the study guide that I didn't cover or anything like that?
Somebody told me, I forgot, maybe that's what you have planned for us today, that we're gonna go over chapters 1 through 7 or 1 through 6.
I'm going to talk about a few things that you should focus on from that. I mean, I don't have time to go over everything because I want to talk about the more applied questions, and then I'll go back and point out some things that you should review from the earlier chapters. So let's see. The couple things I asked you to think about, one of them was if a person comes to you and their goal is weight loss, and they ask you, is it better for them to walk at a slow pace rather than run so that they stay in their fat burning zone? I wanted you to have an answer for them. Does anybody have a good answer for that? Okay, well, I'm not just going to answer it for you at this point, so.
I know running is good, but I forgot like how to explain that as a better way to explain that. Like,
So the idea of walking instead of running so that you're in the fat burning zone, because at a lower intensity we burn more fat, right? Higher percentage of fat. So is that the best strategy for weight loss, to work at a low intensity?
Earlier in the semester, you said that the best strategy for weight loss was to just burn more total calories. So we said that higher intensity exercise is usually better because you burn more calories. But you said just with the logic of just using fat, sitting in our chairs wouldn't be enough, or that would be the best way to burn fat, but that's obviously not true. So burn more total calories is the answer.
Right, so it is true that the lower the intensity you're at, the higher percentage of the calories you're burning are coming from fat, but you're burning a lower total calories, right? So if we went with the idea of the fat burning zone being the best way for you to lose weight, then sitting in your chair would be best of all, because that's when you're burning the highest percentage of fat. So if someone is trying to lose weight, they want to burn as many calories as possible. It'll be a lower percentage of fat, but it'll be a higher amount of fat. Does that make sense? I mean, I went through that explanation with you guys a long time ago. It's an important thing to understand, because a lot of people think the fat burning zone is where they want to be for weight loss. Okay, that should be something you should be able to pretty easily explain. Okay, the other thing I asked you, I gave you the drawing of the workout, right? I did that in this class, right? Okay.
The chart.
Let me draw it up here again for you. Actually, in this class, I didn't do it like that. Something like that. Something like that. Okay, so this was time. It was oxygen consumption. I said the black line is oxygen requirement and the pink line is oxygen consumption. Can someone explain to me what's happening here?
Would this be like a HIIT workout?
Mm-hmm.
So From what I got, it's like they're starting to work out, and so they're at an oxygen deficit. And then it looks like they're taking a break, or they're finding steady state, and then they're taking a break, and then their oxygen consumption is more than their requirement, and it's like going.
Are they hitting steady state in here somewhere?
No,
No.
No, there's no steady state.
not steady
If
state.
they were hitting steady state, they wouldn't be doing a HIIT workout, right? Because steady state is aerobic and a HIIT workout is anaerobic. So there's no steady state in here.
Okay.
So if these are the work intervals, right? And these are the rest intervals. Okay, can someone give me some more information about what's happening?
Would this HIIT workout have the individual be in a constant flux of O2 deficit and EPOC?
Where is the deficit?
The deficit is where the black line is higher.
Okay, so this would be deficit,
Yeah, and then
the work intervals.
yeah, and then EPOC would be where the pink line is higher.
Yeah, but like Justin said, this individual's doing a high intensity interval workout, so they're always at a higher oxygen requirement throughout the entire workout. So they never dip all the way back down to like the original, if that makes sense.
Right, so this is the recovery. What do you think they're doing during this recovery?
Maybe like some type of active recovery, like jogging around, or like, just clearing that CO2. So they're obviously not doing squat jumps. They're doing something that's helping them use their type 1 fiber so they can clear that CO2. And we're using a crossover concept there too.
Does it look like this person is sitting down or standing still? Or does it look like they're moving around?
They're
They're still
moving.
moving around.
Right, if they were sitting down or standing still, this requirement line would come all the way back down to resting levels.
Yeah, but EPOC would be much greater, right? They'd be,
Right.
they'd be consuming a much more oxygen than required if they were sitting down or going back to complete rest.
So if I drew it like this, and they were coming all the way back down to resting levels in between, that basically means they're standing still during recovery. Okay, because the requirement, so this is resting oxygen requirement. Okay, their recovery oxygen requirement is here, and their peak oxygen requirement during their highest intensity interval is up here. So during their recovery, they're not completely resting, right? They're still working at this intensity. Does that make sense?
Yeah.
So
That decrease at the end means that they sat down.
yeah, so this, they either cooled down or they sat down. This was the end of their workout.
Okay.
Down here. But you can also see that each of their intervals was about the same intensity, right? I could have drawn it so that they have a shorter rest, because here, like the rest period is about the same length as the work period, right? I could have drawn it so that the rest is shorter, and then each subsequent work interval is going to be a lower and lower intensity. Do you see the difference? So this is a decreasing intensity in each interval because the rest intervals are shorter. Here I have longer rest intervals, therefore each work interval is staying at a high intensity. Does that make sense?
So just to clarify, it would be like physiological fatigue for the top one, and then metabolic fatigue for the bottom one.
Yes, they're both physiological fatigue. It would be more mechanical fatigue in the first one and more metabolic fatigue in the second one.
Okay.
They're both physiological.
Right.
Yes, so when you're looking at something like this, interpreting something like this, you should pay attention to how long the work and rest intervals are. Okay, so if these are minutes, this is like a 1 minute work interval and a 1 minute rest interval, and a 1 minute work interval and a 1 minute rest interval. If you look at this one, the rest interval is shorter, and then each work interval is getting lower in intensity. Okay, so we're not just looking at the comparison between the requirement and the consumption. We're looking at the rest compared to the work, and then how the work is changing as the time goes along. Right? So you need to be able to interpret something like this, or draw something like this. If I were to, well, you're not gonna be drawing on the test, but ideally on a test, you should be able to, if I give you an example of a workout, draw the requirement and consumption graphs and understand them. Does that kind of make sense? Okay. Okay, let me give you this example. We have Melanie and Emily are both jogging on a treadmill. Emily is trained, Melanie is not. They're both jogging on the treadmill, and they're increasing their speed from 6 miles per hour to 7 miles per hour to 8 miles per hour. What is happening to Emily's heart rate and why? Anyone can jump in and answer.
Doesn't it decrease because she's trained?
Okay, does everybody agree with that?
Wait, could you say who's trained and who's not trained again? I'm so sorry.
Emily is trained, Melanie is untrained. Do you guys want me to repeat the question? Okay, Emily and Melanie are both jogging on a treadmill. Emily is trained, Melanie is untrained. They're increasing their speed from 6 miles per hour to 7 miles per hour to 8 miles per hour. What is happening to Emily's heart rate and why?
It would go lower, right?
Why? Why?
Because she would already have adaptations to she would have a higher vagal tone, meaning a higher PNS activity. Meaning, I don't know.
Is it because her stroke volume is increasing? Because of the 4 components, the EDV is increasing and the ESV is decreasing.
So you're saying her heart rate is decreasing?
Oh,
Her
no.
heart,
I'm asking about her heart rate.
yeah, heart rate would not decrease during exercise. It would still increase because the muscles and everything are still demanding oxygen, which needs to be consumed. But in comparison to an untrained individual, those numbers might be different.
Okay, my question was, what is happening to Emily's heart rate and why? Gwen says it's increasing.
I feel like anybody's heart rate would increase with exercise regardless of how fit you are, but she would be starting off with a lower heart rate because she's in a more fit disposition, I guess, but it would increase.
The point you made at the beginning is perfect. So when you guys were first answering this, you were answering it as if it was the training question, comparing the trained person's heart rate to the untrained person. Trained person, Emily will probably have a lower heart rate than Melanie because she's trained. But I didn't ask you to compare her heart rate to Melanie's. I asked you what is happening to her heart rate. She's increasing her speed from 6 miles per hour to 7 miles per hour to 8 miles per hour. Her heart rate has to increase as intensity increases. So this is an exercise question, not a training question. So in a training question, we're comparing the trained person to the untrained person. In an exercise question, we're looking at what happens in response to increasing intensity of exercise. It does not matter if the person is trained or untrained. If they're increasing intensity, all of the answers are the same. Whether you're trained or untrained, heart rate is going to increase because of increased sympathetic nervous system activity, sympathetic cardiac nerve, epinephrine. That happens whether you're trained or untrained. Okay, stroke volume goes up because of venous return, because of the 3 venous return mechanisms. That's a response to exercise. That happens whether you're trained or untrained. Okay, so maybe Emily's heart rate is down here and Melanie's heart rate is up here, but as they increase their speed on the treadmill, their heart rates are both increasing. Do you understand the difference?
Yeah.
Okay,
The whole
so make sure when you are asked these questions, if you see the word trained, don't automatically go to the training side of the table. Okay, listen to what the question is asking. If intensity is increasing and I'm asking what's happening during the intensity increase, doesn't matter if the person is trained or untrained. You're talking about how the body responds to exercise. The body responds to exercise in the same way, whether you're trained or untrained. Okay, if we're comparing the trained person to the untrained person, it'll be at the same intensity. It won't be at an increasing intensity. Does that make sense? So if I said, Emily and Melanie are both running on a treadmill. Emily is trained, Melanie is untrained. They're both jogging at 6 miles per hour. How does Emily's heart rate compare to Melanie's heart rate? Then what would it be?
Lower.
Most likely lower because
the submax stroke volume is higher.
Finish that thought.
Which means that it's like more efficient. It can deliver more blood throughout the body.
Is there another term you can throw in there for that?
A cardiac output.
Okay, so they need to deliver the same cardiac output because they're consuming the same relative amount of oxygen, right? The trained person can do it with a lower heart rate because their stroke volume is higher. Okay, at this point, it probably doesn't have anything to do with the parasympathetic activity because if you're jogging at 6 miles per hour, you're well above that level. You're well above 100 beats per minute, most likely. Okay, what else can I ask you? I want to ask you something about lactate threshold. Think about this for a second. Let me think about that question. Okay, let's go back to some of the older information and review a little bit. Speed characteristics, force characteristics, energy system characteristics. Pam, can you remember force characteristic?
Motor unit size.
Okay, can you explain it, please?
Yeah, so the bigger, the more attachment, so the more attachments to the neuron, it means there's more mitochondria, more actin, and it's able to produce more force, more peak force.
Does mitochondria contribute to that?
I mean, myosin and actin. I don't know why I said mitochondria.
Okay, and what do you mean by connections to the neuron?
Because it's the alpha motor neuron, so it innervates more, so it's bigger, I guess.
Innervates more what?
I don't have the word.
What does it mean to have a larger motor unit?
More fibers connected.
More fibers, right? So a motor unit is one alpha motor neuron and all the fibers it's connected to. So having a larger motor unit means more fibers are connected to one neuron. So that enables you to produce more force because you're activating more fibers, which means more cross bridges and more power strokes. Good. Justin, can you explain a speed characteristic?
A speed characteristic would include ATPase type. So, for example, if you have a faster ATPase, ATP would be broken down faster, then the energy would be, and more energy would be used to bring back the myosin head back to 90 degrees faster, and thus being able to produce more power strokes faster.
Okay, I'll take that. Good. Christian, can you give me another force characteristic?
Wouldn't be calorie density, I think. No.
I missed what you said, something density?
Oh, a capillary density?
Capillary density, how would that be a speed characteristic?
When vasoconstriction or like any kind of constriction happen, it creates a more heavy blood flow, which like causes it to go quicker along those lines.
So you're close. You're close. The capillary density is going to be more of an energy system characteristic because that's going to involve the delivery of oxygen.
Okay.
AJ, can you give me a speed characteristic?
Neuron size, because the larger the neuron, the faster you can transmit the action potential.
Good.
Which equals faster grasp. Yeah.
Good. Evelyn, can you give me a speed characteristic, another speed characteristic?
Another speed characteristic. We've already went over neuron size and ATPase, right?
Oh, did we do all three speeds?
No, we're missing one more.
Are we?
I think so.
Yeah, we're missing one.
Did we
Okay.
do sarcoplasmic reticulum?
No.
Oh, okay, you're right. That's the one that's missing.
There you go.
Thank you, Rachel. Rachel, you want to go ahead and explain that?
So our sarcoplasmic reticulum is more dense, and remember the sarcoplasmic reticulum, that's where calcium is released from. So that means that it's going to be able to send out more calcium, which binds to troponin, which is going to pull tropomyosin off the binding site faster, which means that if we're pulling tropomyosin off the binding site faster, then we're going to be able to cross bridge faster and thus subsequent power stroke faster and thus produce force faster.
Good. So remember that speed is now, when we use the term speed characteristics here, we're not referring to how fast you can run. We're referring to how quickly the fiber can achieve peak force. So any characteristic you're describing as contributing to speed needs to get us to peak force faster. Any characteristic you're describing as a force characteristic needs to help us produce a higher peak force. And that'll be through cross bridges and power strokes. Okay, the energy system characteristics help determine whether the fiber is good at using oxygen or not. So that's going to be the capillaries, the mitochondria, the myoglobin, and the enzymes. We good on those? Okay, the reflexes. So you do need to know the reflexes, but just the basics of the reflexes. You're obviously not going to need to draw them. You're not going to need to describe them in too much detail. What you need is, let's see, we have the stretch, reflex. When does a stretch reflex occur?
Every time you stretch a muscle.
So it occurs immediately with every stretch. What's the sensory receptor?
The annulospiral.
That's the sensory neuron.
Muscle spindle.
Okay, what is the sensory neuron?
Annulospiral.
Sends what kind of signal?
Afferent excitatory.
And what does it do?
It contracts. So it's negative feedback.
So it's going to depolarize or hyperpolarize?
Depolarize.
Depolarize.
The alpha motor neuron of muscle being stretched, causing it to contract. What kind of feedback?
Negative.
Negative. Because it's canceling the stimulus.
Okay, so that's basically what you need to know about the stretch reflex. Autogenic inhibition with a stretch stimulus. When does it occur?
10 seconds after a static stretch.
Okay, be careful not to say 10 seconds after a static stretch, because that means you do a static stretch, you walk away, and 10 seconds later this kicks in, which is not what you're trying to do. What's the sensory receptor?
PTO.
PTO.
Golgi tendon organ.
What kind of signal does it send?
Afferent
Inhibitory.
Which causes?
Relaxation in the muscle.
So we're going to hyperpolarize the alpha motor neuron, the muscle being stretched, which is going to cause
Muscle relaxation.
relaxation, which is what kind of feedback?
Positive.
Positive.
Because it's enhancing the stretch.
Okay. Then we have autogenic inhibition with a contraction stimulus. When does this happen?
Maximal contraction.
Man, that was supposed to be black lettering. No, stop. Messed up my colors. Sensory receptor.
GTO.
Sends what kind of signal?
Afferent inhibitory.
Causing
Causes relaxation.
Hyperpolarization.
Be stretched.
Yeah.
hyperpolarize the alpha motor neuron of the agonist, causing it to relax. What kind of feedback?
Negative.
As we're canceling stimulus. Oops. Okay. Then reciprocal inhibition happens when?
With
Every
every
voluntary contraction.
Sensory receptor,
Muscle spindle.
sensory neuron,
Flower spray.
Right.
sends what kind of signal?
And afferent inhibitory to the alpha motor neuron of the antagonist.
What does it do to the alpha motor neuron?
Causes the alpha motor neuron to hyperpolarize.
Okay, causing it to
Enhanced contraction of agonist.
what's the antagonist going to do in response to the hyperpolarization?
Relax.
Relax. Yeah,
What kind of feedback is this?
that's positive.
Because it enhances
Do we have to talk about the gamma motor neuron?
Oh yeah. Alpha motor neuron. Yeah.
You should know that the gamma motor neuron is involved in this one. So here's the thing. I'm not planning to ask you. Well, I'll just decide right now. Okay. I'm not going to ask you to describe a reflex in detail, but you'll have to answer questions about it. So you should know which one involves the gamma motor neuron. You should know which one happens immediately with a stretch, which one happens after 10 seconds of a static stretch, which one happens during a maximal contraction, which one involves a flower spray, which one involves annulospiral, which ones are positive, which ones are negative. So you need to know the basic information about them, but also be able to answer them in a more applied situation. So for example, a person is doing, let's say Pauline is doing her 1 rep max testing, and she completed 2 attempts, and now she took her 3 minutes rest, and now they increased the weight, and she's going to try to press this one, and she can't. What reflex is occurring?
Autogenic inhibition with
contraction stimulus. So that's the GTO determining her 1 rep max, saying this weight is too heavy for you. Okay. If she went and did resistance training for a month and came back and retested her 1 rep max, and she was able to press that weight that she failed on last time, what happened?
The GTO became less sensitive.
And what's the term for that?
Disinhibition.
Disinhibition.
Oh my
Okay,
God.
so you could explain that and apply that to this example. Okay, what if Pauline during her workout is doing reps of a bench press, and she does her 9th rep and her 10th rep, barely struggles, and then on her 11th rep she failed? What happened?
Wouldn't it be fatigue?
Fatigue?
Can you be more specific? Fatigue is a very general term.
ATP or PCR depletion.
Lactic acid.
Well, that's a good question. We decided it wasn't the reflex. We said it was fatigue. So which fatigue is it? Which system are we most likely in on rep 11?
Glycolysis.
Glycolysis.
So what's the cause of fatigue?
Lactic acid.
And hydrogen accumulation?
And inorganic phosphate accumulation.
Yes, and can you explain those in detail? 3 ways hydrogen causes fatigue in detail that's causing her not to be able to produce that amount of force.
Competitive inhibition is one of them.
Mm-hmm. Yeah, so we don't need to do it right now. I mean, we can if you want to. Do you guys want to review the causes of fatigue from hydrogen? Or are you okay with that? I'm going, I mean, I know you guys have it written down.
Mm-hmm.
The question is, can you come up with it from your head?
Can we review?
Sure.
Quickly.
Sure. Armand, can you explain competitive inhibition, please?
Yeah, so instead of calcium binding to troponin, hydrogen binds. So the binding site stays covered, so the power stroke can't happen.
Good. Nick, can you explain another cause of fatigue from hydrogen?
I'm trying to remember the other 2.
Nick, can you do one?
Oh, you're okay. When we have hydrogen accumulation, it lowers pH, and that inhibits PFK, which slows down glycolysis, which slows down ATP production. And we have mitochondria. Well, it slows down production, and we can't create ATP or go through the redox reactions.
It's not necessarily related to the redox reactions. If we have less ATP, it slows, and we need ATP to go through that muscle contraction cycle, right? We need the ATP to bind to the myosin head to get us out of the cross bridge. So it doesn't need to relate to the mitochondria at this point. It's just that muscle contraction cycle. We need the ATP for that. So it's going to slow us down in that muscle contraction process, which to us is fatigue. We're having trouble recruiting the same amount of fibers that we were before. Tatiana, can you do the other cause of fatigue from hydrogen?
Do we already say decreased blood pH? Is that
We said blood pH inhibiting PFK,
okay? And competitive inhibition, right?
and we did competitive inhibition.
Is the other one the inorganic phosphate accumulation?
No, the other cause from hydrogen.
Oh,
There's 3 for hydrogen. The decreased pH inhibits something else.
oh, that's right here. Okay, let's see. It inhibits the glycogen phosphorylase, which then inhibits the glycogenolysis, and then glucose becomes less available, and it slows down glycolysis and impairs ATP production and muscle contraction.
Good. Good. And then we have the inorganic phosphate accumulation, which inhibits the calcium release. So again, we have fewer cross bridges available because the binding sites are going to stay covered. Okay, so it's not likely to be just me asking you to explain the causes of fatigue and glycolysis. It's more likely to be me giving you a situation and you have to figure out what's happening. So now I can give you a situation and you have to figure out if it's a reflex that's stopping you, if it's PCR depletion that's stopping you, if it's hydrogen accumulation that's stopping you. So you need to be able to analyze the situation and figure that out. Okay. All right. Oh, Rachel reminded me that I forgot to cover the redox reactions with you guys. So does anybody remember the redox reactions well enough to explain it?
Is that with the cytochromes, the ETC? Gosh. Okay.
I think I can do it.
Okay, Nicole, go ahead.
So it's when the electron is passing through each cytochrome, which creates ATP, and when the electron is holding the, hold on. When it has the oxygen, it's reduced, and when it releases, it's
not the oxygen.
The electron, sorry.
The electron. So what's holding the electron?
The hydrogen?
What's passing the electron?
Oh, dang it.
Emily, you want to help her?
The cytochrome. So basically a redox reaction is basically explaining what's happening to the oxygen as it's being passed through each of the cytochromes. So
not the oxygen.
The electron, sorry. So when it has the electron, it's going to be, so it's redox. So it's going to be reduced because it's more negatively charged. And when it gets passed on, it's going to be oxidized because it has less of a negative charge. It's not necessarily positive, but that cytochrome becomes oxidized because it lost that electron, and then it just gets passed on until the byproduct is H2O.
And what is the purpose of this?
To create ATP.
Well, we create energy. So the redox reactions create energy, and we use that energy to create ATP. And what's the term for that?
Oxidative phosphorylation.
Oxidative phosphorylation. You should be able to write the equation with the enzyme. What's the enzyme for oxidative phosphorylation?
Cytochrome oxidase.
ATP synthase.
ATP synthase. Cytochrome oxidase is the enzyme for the redox reactions.
Oh,
okay. Okay. What is the rate limiting enzyme for Krebs?
Isocitrate
Dehydrogenase.
What is the rate limiting enzyme for glycolysis?
Phosphofructokinase.
which you can now abbreviate, by the way.
PFK.
Okay, so make sure you can understand and explain the redox reactions, what reduction means, what oxidation means, and all that. Let's review hormones. What effect would you expect epinephrine to have on glycogen synthase? Activate or inhibit?
Inhibit.
Okay, why?
Because glycogen synthase is, well, think about it like this. Epinephrine, it's catabolic. So it's trying to break down you're trying to make your fueling sources and your nutrients as available as possible because you're working out. So as you increase exercise intensity, you release epinephrine. So glycogen synthase is over synthesizing or building the glucose into glycogen for storage. So that would be inhibiting it.
Perfect. So in order to answer these kind of questions, you need to know what the hormones are trying to achieve, and you need to know what the enzymes are trying to achieve and see if they match up or not. Okay, if they match up, it's going to be activated. If they don't match up, it's going to be inhibited. Okay, what effect would glucagon have on lipoprotein lipase?
Inhibit.
Inhibit. Glucagon wants to take your substrates out of storage. Lipoprotein lipase takes your fat out of storage. Good. What effect would insulin have on glucose 6-phosphatase?
This would inhibit.
Inhibit.
Okay. Insulin wants to decrease glucose levels and put everything into storage. Right? Glucose 6-phosphatase is the enzyme for gluconeogenesis, which is going to create glucose, which is not what insulin wants. Okay, so make sure you review all of that terminology. Alexis, do you remember what GLUT4 is? It's okay if you don't.
Sorry,
That's okay.
I didn't realize I was muted. Yeah, so it's a glucose transporter. So you don't want insulin to be activated during exercise, but GLUT4 is activated during exercise. And the reason why that one is activated is because you need that glucose transporter specifically, not insulin, and you don't want insulin to be activated in order, because it's not specific to the muscle, the exercising muscle. It promotes storage, and also the muscles become more sensitive.
Okay, good. So you answered my next question.
Sorry.
No, you're fine. So what are the 3 reasons we need insulin levels to decrease during exercise? So Alexis answered that for you. Good. Okay, let's go way back to the initiation of muscle contraction and combine it now with the initiation and propagation of the action potential and the sliding filament theory. So remember when we first learned it, the action potential part we learned separately. And I said at the end of the semester, we got to put all that in. Okay, so now we've got to go from describing the resting membrane potential, describing what the brain is sending, how we initiate and propagate the action potential through the initiation of muscle contraction through the sliding filament theory. Does anybody want to attempt that? Starting with the resting membrane potential.
I could try.
All right, Rachel, go for it.
All right, so at a resting membrane potential, we're at -70 millivolts, which means we're more positive on the outside and more negative on the inside. We have potassium on the inside and sodium on the outside, and it has potential, meaning we have a difference in charges. And so basically what we need is we need to reach a positive 15 millivolt threshold in order to send an action potential. We do that via the process of summation, which is when we send graded potentials, like which are weak signals that add up to reach that positive 15 millivolt threshold. When we hit that positive 15 millivolt threshold, we accomplish the goal of depolarization, which is when now we're at negative 55 millivolts. And basically then what happens is that then our sodium gates open. And this is what triggers, when the sodium comes in, this triggers the action potential to travel down the neuron, going through the nodes of Ranvier and jumping over the myelin sheaths. And when it reaches the axon terminal, it causes the release of acetylcholine into the neuromuscular junction. And when the acetylcholine binds to the plasma lemma, and then that triggers the action potential to be sent down the transverse tubules to the sarcoplasmic reticulum, where calcium is released, and the calcium goes to the troponin and binds to the troponin, and then pulls tropomyosin off the binding site. And then when it pulls tropomyosin off the binding site, then we can cross bridge, and then we can power stroke, which means we can produce force. And then, while this is happening, when calcium binds to when acetylcholine binds to the plasma lemma, what's happening is then the potassium gates open. So potassium leaves the cell membrane, and it's going on the outside. So now our cell membrane is hyperpolarized, which means it can't receive any signals. So now we need our sodium potassium pump. So this basically returns our levels back to negative 70 millivolts with potassium on the inside and sodium on the outside. And now we can receive more signals from, so we can, yeah.
Awesome job, Rachel.
Thank you.
You're not quite done. You got to finish what happens after the cross bridge.
After the cross bridge, okay. So, okay, let me think this through. So when we cross bridge, then, we're going to the sliding filament theory, right? Mm-hmm. Okay, so we have ADP and inorganic phosphate on our myosin head. So first we have the release of inorganic phosphate, which triggers the power stroke, which is when our myosin head folds into a 45-degree angle, pulling actin along with it. And this is when also so it pulls in towards the middle with actin with it. Oh, there's one other thing. What is it? Pulling actin along with it. I'm trying to think. There's one other thing.
To the center of the sarcomere.
Yeah, to the center.
45-degree angle. You're fine.
Okay. And then what happens is then we release ADP. This causes rigor state, which is when the myosin head is locked in contraction at a 45-degree angle. And so then we have to get out of rigor state. So a new ATP comes and binds onto the myosin head. So then this initiates, we need to use our ATPase to break that down. So we use the ATPase, so it's ATP arrow, ATPase, that's our enzyme, and it turns into ADP, inorganic phosphate, and energy. This release of the energy causes the myosin head to go back to 90 degrees with ADP and inorganic phosphate on it, and then the process continues.
Nice work. Very good. Very, very good.
Yeah.
So practice that, everybody, for Rachel. Practice that. And tell me what could stop that muscle contraction cycle from happening. Anybody?
You said what stops like muscle contraction?
What would stop that muscle contraction cycle from happening?
If the brain stops sending a signal.
Yeah.
Okay, so how would that stop it from happening?
It wouldn't initiate. Oh, you could go ahead.
Oh, I was gonna say the brain would stop sending signals, and the calcium would get pumped back into the sarcoplasmic reticulum.
Finish.
So it would mean that no calcium would equal stopping stops binding with troponin.
So that what happens? If the calcium's not binding to troponin, what happens?
So there's no actin and myosin cross-bridging?
Yeah, so we can't cross bridge, so we can't power stroke. Okay, so make sure on the final, I'm not going to be there to prompt you to continue explaining. Okay, make sure you explain it all the way. So just saying that the brain is not sending any more signals doesn't fully explain why the muscle contraction is stopping. Got to go all through the details and explain why there's no calcium released, the binding sites stay covered, therefore we can't cross bridge and power stroke. It's going to block the muscle contraction. Good. What's another reason the muscle contraction cycle would stop?
The Z disc would be in contact with the myosin.
Okay.
And if that happens, that there's no ability for a power stroke to occur, and the myosin head could possibly remain in regular state.
Good. So remember when we first learned this way back in the beginning of the semester, I gave you those 2 reasons that would stop muscle contraction. I said at the end of the semester, this list is going to get a lot longer. Okay, so tell me some other things that could stop the muscle contraction or slow down the muscle contraction.
Well, fatigue could do this.
Can you be more specific?
Yes. So it depends on which metabolic system you're in, but specifically for like glycolysis, when you think about it, like we have to have like, for example, like with competitive inhibition, we need calcium to bind to troponin. So this is like the similar thing that we were talking about with regards to if calcium doesn't bind to troponin, there's going to be no cross bridges and no power strokes. And that's only one of them. Then also like hydrogen accumulation can affect that as well. And inorganic phosphate accumulation, that prevents the release of calcium. When it comes to glycogen depletion, this could do that as well as PCR depletion.
Could the decrease of blood pH also relate to this because it affects like glycogen phosphorylase, which would...
So that'll be part of this. So assuming you have an explanation for each of these, there will be a very detailed explanation, 3 ways hydrogen is causing fatigue. And fatigue means we're decreasing or stopping our muscle contraction, right? So that's why this goes in here. So yeah, that's part of the explanation for this. And you have an explanation for all of these, but we can add more to this list.
Delayed onset muscle soreness be one of them?
Specifically what?
The actin is less stable.
Why?
Because it's been damaged. So the Z discs are what maintain the actin. When it's damaged, it's not as stable, so the cross bridging and power strokes are not as efficient.
Very good. What else?
Oh, damage to the plasma lemma, because the plasma lemma is where the acetylcholine binds to. And if it doesn't bind to the acetylcholine, then we're not going to get the subsequent steps after with like the release of like calcium and all of that.
Good. You think of anything else?
Okay, I don't know if you could put central nervous system fatigue. No, that's more psychological.
What about running out of like glycogen? Or no, you put that. Never mind.
We have glycogen depletion. There's one more main one I'm looking for. Excuse me. A bunch of small ones we could put on here. One more main one I'm waiting for.
Lactate threshold?
Yeah.
Maybe?
Explain.
Oh. That might fall under something else. Because that's like due to the accumulation of hydrogen.
So that falls here.
Okay.
Does the skeletal pump or any of the venous return pumps have to do with anything, venous return mechanisms?
They won't cause fatigue. I mean, they won't interrupt muscle contraction. Do you guys want a hint?
Yes,
Would
please.
it be muscle cramp? I don't think so, right?
A cramp?
Or muscle cramps? I don't know if that would. I know it's lack of oxygen. I don't know if that would technically count.
Yeah, you could put lack of oxygen here.
Would it be immobilization? Because I mean, technically, you're not contracting.
You could argue that. Think through the reflexes.
Oh.
The autogenic reciprocal contraction, inhibition contraction.
Wow, 11.
So that autogenic inhibition can definitely shut down a muscle contraction, right? Okay, we don't need to go any farther with this. We could come up with some more, but you get the idea. There are a lot of things we learned about that could interrupt the muscle contraction cycle. Yes? Okay. And be able to list a few of those and explain them. Okay, you don't have to memorize that entire list. Just be able to think of a few things and explain them. Okay. Can someone explain to me the length tension relationship? Armand, you want to try?
Yeah, so it's the longer the muscle is, the less force production there is, and also if it's too short, there isn't a lot of force production. And the reason for that is when it's lengthened, the actin and myosin aren't overlapping a lot, so not as many power strokes happen. And the one is too short, the reason is the Z discs are too close, so they can't move in any closer.
Mm-hmm. Very good. So you can cross bridge in that situation, but you can't power stroke.
Yeah.
Good. So instead of asking you to explain the length tension relationship, I'm more likely to give you a situation to apply it. So can anybody think of a situation where they could apply that?
So like why you shouldn't do static stretching. So like let's say you had a track athlete and they were at a meet and they were in between events and then they go do static stretching and then they see a decrease in performance because of that static stretching. You would talk about how there's like less cross bridges, less power strokes because of how like the length tension relationship, the Z discs are pulled apart. So you could talk about that.
Mm-hmm.
You could also mention, like, for example, on the exam, if why someone couldn't press all the way up from the very bottom of an exercise like a bench press because there's no ability for the muscle or the cross bridging and power stroke to happen if it's.
Right, so it's getting stuck at the bottom of the bench press. So how could you determine if someone is stuck at the bottom of their bench press, how do you know if it's because of the sarcomere being pulled apart or because of autogenic inhibition or because of hydrogen accumulation? How do you know?
Because the pectoralis major muscle is stretched at the bottom of the bench press. So, well, same with the triceps.
But there could also be a huge accumulation of hydrogen and lactic acid, which would be causing fatigue.
So how do you know which one's happening?
I think it depends on how long they've been doing the exercise for. Because like if they're just going for like 1 rep and that's it, that's their entire workout, then obviously they're not fatigued. So
Yeah, it's not going to be hydrogen accumulation if it's their first rep. Good. Good. So these are the types of things you need to be able to think through. These are the kind of applied situations that you're going to get on the test that you need to analyze and use some terminology in explaining what's happening. Okay. So you guys have questions for me?
Oh, okay. I was talking to Bobby and we were discussing like the biceps curls and whether or not why it wouldn't be, because you know how some people they do biceps curls and they're like they do them super fast because they're trying to get that pump. Why like how could you do that eccentric overload like based on, you know what I mean?
So if you want to focus on the eccentric contraction, it needs to be heavy, very, very heavy, maximally heavy or super maximally heavy for your concentric contraction. So if you can move the weight quickly, it's not anywhere near your max.
Okay.
So that resistance is going to be too light for what you're trying to achieve. That's more for power. When you lift a lighter weight and move quickly, that's more power training than strength training. I don't have an approximate number of questions on the exam. I have not started writing it yet, to be honest, because I was waiting to decide if it was going to be open note or not, because that changes the entire exam. So I've decided that it's not going to be open note because if I make it open note, I'm going to make the test a lot harder. I'm going to make the questions that you cannot answer from your notes, which defeats the purpose for you of making it open notes. Okay, you want me to make it open notes and leave the test the same so you can find the answers in your notes, and I'm not going to do that. So I think at this point, if I allow you to have your notes, I'm going to make the test a lot harder, and it's not going to benefit you in any way. So I think it's more beneficial for you to leave it the way it is. You know exactly what to study. You know exactly how to study. And I think that is more beneficial for you. Okay. Chapter 9, just the terminology. You have a list of terminology from chapter 9. That's all you're responsible for that. Your test is when?
It's Wednesday at 8 a.m., the 14th.
Okay, thank you.
Sorry,
So
the 13th.
Next Wednesday from 8 a.m. to 10 a.m. So make sure you have access to the internet at that time for your computer and for your phone. It's going to be lockdown browser and Zoom on your phone, just like the midterm was. Okay, make sure your phone is charged or plugged in. So nobody's phone should be dying or turning off at all during the test. You're not going to be allowed to get up out of your chair and go out of the room during the test. So make sure you've got everything you need, just like you would if we were in the classroom. What is the max duration of glycolysis? Is not 2 hours. 2 hours is if you're working aerobically, your glycogen stores last 2 hours. If you're working anaerobically, I didn't give a number. It depends on how far above your lactate threshold you are. So if you're just above your lactate threshold, you can stay there a few minutes. If you're far above your lactate threshold near your maximal intensity, it might be 10 seconds. So 2 minutes is a number we give just in general for the system, but it is a wide range. Okay, RP, you have a question?
Yeah, I remember you mentioning that you wanted to kind of change the format, like the multiple choice and the written, like maybe do 2 parts. Have you decided how it's going to be?
That's my plan. I need to work on it and I'll practice it with the PLFs, because what I've heard from another instructor doing that is it's complicated when you're in the lockdown browser to log out of one test and into another. So I need to test that out. You can have blank paper. You're going to have calculation. So you can have blank paper. Okay, but no notes. And you can have a calculator.
Do you know what calculations will be on there?
There could be an energy expenditure calculation. There could be something, most likely a calculation using the ACSM formula with the speed and grade, something involving that, because we had a really hard time with that on the midterm. And I want to make sure you guys know how to do that. Gwen, go ahead.
I was just wondering if mechanical fatigue was due to micro tears in the muscle.
Fatigue is not, fatigue is not really caused by the tears.
Mechanical fatigue specifically. What is that caused by?
Mechanical fatigue would be like the GTO shutting you down would be mechanical fatigue, or running out of PCR would be mechanical fatigue, because you can no longer use those 2X fibers, and the 2A fibers are not strong enough to produce that amount of force. So the hydrogen accumulation and inorganic phosphate accumulation would be metabolic fatigue.
Okay, thank you.
Yeah, Emily, go ahead. You need to unmute yourself.
The exam is the same format in that it's like one question at a time again.
Yes, the questions will be locked down one at a time, but I'm planning to separate the short answer questions from the multiple choice fill-in. But there also will be questions again that are select all that apply. So make sure you read the questions carefully, because that was a little bit difficult on the midterm, those kind of questions.
Are we doing any extra credit or extra questions on the test?
I'd like to. I haven't figured that out yet. But yeah, and then timing becomes an issue as well. So yeah, if I can figure out a way to do that, I will do that. Yeah, Rachel, go ahead.
Okay, I have a couple questions. Would applied question be like diabetes and how like you can train to make insulin like more sensitive?
If I didn't talk about it in class, I won't test you on it.
Okay, and then beta oxidation, should we review how to calculate that?
Counting ATP from beta oxidation, from fat metabolism, yes.
And then like the theta pyruvate.
And the theta pyruvate, yes. We talked about that. We reviewed that. I didn't use that term, but we talked about it in relation to increasing lactate threshold and how we affect lactic acid production with the mitochondria. That's the same question.
Okay, and then BMR and like all the resting metabolic rate, all that stuff, that'll come back up too.
Yeah, well, you guys did really well on those, knowing those ranges. So it'll be more conceptual with that probably, or applied, like this person weighs this much, what's likely their resting metabolic rate, and be able to calculate someone's resting metabolic rate would be more likely.
For specific like training conceptual questions you'll give us, will you give us like numerical, like 2 to 3 minutes or 15 seconds, or will it be our judgment to figure out what that exercise would result in, basically?
Well, I'll try, I mean, I'm not trying to trick you, I'm just trying to make sure you understand the concepts. So yeah, I'm not sure exactly what you're asking, but yeah, I'll give you situations, like an example of this person's training. If this person trains this way, and then their performance is this, how will that training affect the performance? And you need to go specifically into the adaptations. So this is why you need to be prepared with those 9 adaptations from endurance training, be able to explain how each of those improves VO2 max. And then with the secondary adaptations, how it's going to affect lactate threshold, how that's going to affect performance. Rachel, is your hand up from before, or do you have another question?
One more question. Do you think like we should know about like the size principle and being able to integrate that too?
Yeah, we talked about the size principle and the crossover concept, all relating to the RER and relating to the lactate threshold. All of those things are related. Mhm. So if there are topics from the beginning that I didn't specifically review, it doesn't mean they're not on there. It means if they're on there, it might be like a 2-point question, 1 2-point question here, 1 2-point question there. The ones that are worth the more points and the bigger questions are the ones I went over. Okay. Trying to think. I don't have those study guides in front of me, so. If you guys come up with something else you want to ask me about, I have office hours right now at 11. I have office hours tomorrow from 3 to 3:45. And then I'm also available by email. Okay, and then you have your PLFs. So people tend to spend more time studying the older material and forget to study the newer material. So please spend a significant amount of time on this table, being able to answer questions about responses to exercise and adaptations to training. I tend to have a lot of points for that. Okay, which is one of the reasons I don't want to give you open notes, because if I give you open notes, there's no reason for me to ask you anything from here because you just have it in front of you. You don't need to learn it. Okay, so I want you to learn that stuff. And the neural adaptations and the hypertrophy and the DOMs and all that from these last couple chapters. Make sure you spend some time on that. Rachel, go ahead.
You asked a question about volleyball and what metabolic systems are they in. I was thinking it's glycolysis because like the first, like if you're like a setter or whatever, like that would be like AT-PCR when you start the rally, but like then you would go into glycolysis. But if you're really trained, you could technically do it aerobically, but I don't know how you would go about thinking that through.
So the thing to think about with the sports, and the reason I wanted you guys to think about the sports, is that most sports and most things we do are not just in one system. Okay, the body is very fluid, so it's not like when you're in one system during an event, during an activity, you're in one system and the other systems are shut off. Okay, all the systems are always working, and we're very fluid going in between the systems. Okay, there's not a sudden shift. There's not like a switch turning on and off. We're fluid with all the systems. It's just a matter of that sometimes we're more reliant on one system than the other, and then we shift back and forth. So in most sports, we're going in and out of different systems. Okay, so try not to think of it as so black and white. We're either in this system or in that system. One system's working, the other system's not. So I'm not sure that I mentioned this in here, but when you're doing high intensity interval training, it will improve your VO2 max. Can anybody explain why that would happen? What adaptations would you get from high intensity interval training that would improve your VO2 max?
Well, you would be increasing your lactate threshold. And if you increase your lactate threshold by like increasing your bicarbonate buffer, you're helping yourself clear that lactic acid faster, so you're able to work at a longer intensity without experiencing fatigue. But I don't know.
It causes an increase in VO2 max.
Yeah, that's true. I'm trying to think.
Oh, I forgot to go over those questions at the bottom of the study guide.
Do we improve our VO2 max because it has the same adaptations that we get from training glycolysis? The muscle fibers, hypertrophy. Actually, wait. Let me go back to my notes.
Professor, I was planning to go over those 3 questions in the review sessions. I'm not sure about the rest of us, but I'm going to be doing it.
That'd be great. I'm going to try to get to it in my other classes. I just
okay.
Forgot for this one. So yeah, thank you. Okay, so let me just answer this real quick since we're out of time. When you're doing high intensity interval training, you get increases in your VO2 max because of this. What does this mean to you?
Oh, right. Oh my gosh.
if you're doing high intensity interval training, you're activating your 2A and your 2X fibers. Are the type 1 fibers resting?
No.
No, because of the size principles of early recruitment, those are getting activated as well. So even though the workout you're doing is focused on the fast twitch fibers, the slow twitch fibers are also getting activated and trained. When you activate the type 1 fibers, they respond not with hypertrophy, but with those, with the mitochondria, capillaries, enzymes, and myoglobin. They become more efficient at using oxygen. So you might see a little bit of hypertrophy in there, but it's mostly those energy system characteristics that are going to improve, which is going to improve your VO2 max. Okay, which is why high intensity interval training is one of the best types of training you can do, because you get adaptations across the board. All right, so I'm going to stop there. It's been a pleasure working with you guys. I'm sorry that the semester turned out to be remote and I didn't get to interact with you guys and throw Jolly Ranchers at you and play with you a little bit more, but I thank you guys for continuing to show up to class and putting in the effort and the work to learn the information. And there are still, what's it called? The evaluations are still open for you if you want to fill those out. It's there till the end of the week, I think. And I'm available by email if you want some help. Take advantage of your PLFs. Thank them for all the effort they're putting in. Okay, and I will see you guys. What day is it again for you guys?
Wednesday, I think.
Wednesday. All right, you guys have a great day.
Thank you so
Thank you,
much.
Professor.
I'll start at 11 if you want to come back.
Bye, Professor. I'll talk to you later.
Okay, thanks, Mira.